Good afternoon. My name is Michael Kroll, and I'm going to be talking to you today about additive manufacturing, making more of your chairside scanner. Good afternoon. My name is Michael Kroll, and I'm going to be talking to you this evening about additive manufacturing, making more of your chairside scanner. What you're going to find in this presentation is my views on how we can kind of advance digital dentistry in our practice beyond just the simple in-office milled crown or the crown being sent off to our dental laboratory. One thing I always present at the front of my lectures is understanding there's always things to learn, and we also have a lot of experience that I may not have experienced yet. So one thing that I always have to say is we have to have a tension between our hubris and our humility when we're doing these types of presentations. To understand that we have things to learn, but also that we've learned a lot along the way. So I'm going to first go over my disclaimer. The views expressed in this presentation are those of myself and do not reflect the official views of the Department of Defense or other departments of the United States government. I do not have any financial interest in any of the companies, materials, or products that I discuss in this presentation. So what I'm going to be talking to you about is going through how our 3D scanners work, what some of the different common file extensions are, what are the different 3D printer technologies that we see most commonly in the dental practice, why we would use a 3D printer in our own office, and first starting with once we get a 3D printer, what's going to be the immediate thing we first try to do? We'll probably try to print a model from one of our intraoral scans. Then beyond that, we obviously know there's things that we can send to the lab like a crown. But if we do 3D printing in our office, there's other ways to capture our return on investment from that 3D printer. Things that are much more lucrative and will pay off that 3D printer much faster. Things like night guards, sleep devices, orthodontic clear aligner therapy, and guided implant therapy. So I'd be remiss if I didn't mention what CAD/CAM actually is. So we often think of CAD/CAM when we think of CEREC, or we think of something like the Emerald scanner and Plan Mecha system. We think of computer-aided design and computer-aided milling, but in actuality, computer-aided design is the application of the computer and graphics software to help our product design from conceptualization to documentation and final production. The computer-aided manufacturing is the use of computers in the manufacturing, planning, and control of our process. So it can happen in two different ways, right? We can have additive and subtractive methods. So when we look at our subtractive methods of CAD/CAM, that's more along the lines of our in-office milled restorations. When we start looking at additive types of restorations, that would be something along the lines of 3D printing. But also we have to know how the evolution of our digital scanners actually worked, okay? So for this, I'm going to go ahead and I'm going to break down just one company. I'm going to just look at the evolution of intraoral scanners from Dentsply Sirona. So if we look, we started with something called the RedCam, something that used a focused beam of light. We had to get very, very close to the tooth within 9 millimeters. We had to place an anti-reflective coating or a powder on top of the tooth in order to capture an image because the camera would calculate the speed of the light coming back to the camera, stitch images together, and give us a 3D representation of our tooth. As digital scanners became better and better and better, we had things like the blue cam. So use a different type of light, better software, auto image capturing, which allowed for a greater focal distance. Now, when we went from the red cam, which was primarily just for inlays and onlays, we went to the blue cam and this newer software, and this gave us some added benefits in the dental practice where we could integrate maybe some dental implants. We could integrate some quadrant dentistry in some anterior cases. And this is really when dental laboratories started to take off and actually accept our digital scans to the dental laboratory for a completely CAM type of production model. Then introduced in about 2010, 2011 was, the first iteration of our color scanners. I believe, iTero came out in 2007, Trios came out around 2010, OmniCam around 2010, 2011. we started looking at some of these scanners, we started to have live color image capture, where we would have a color image show up on the screen, a larger focal distance, and the ability of our camera head to do what's called a free-form type of scanning technique. We could move it in any direction we wanted, and as long as those images of the camera head were close enough together, the images would stitch. Now we're on to the newest model, which is what's called the prime scan. For other manufacturers, we've got the Trios 3 or the Trios 4. We've got the Emerald or Emerald S scanner. We have the CS3700. We have the new Medit i700. All of these cameras kind of work on slightly different principles, but they start to really be the first generation of color scanners, which really open the door to more than just single unit posterior dentistry, quadrant dentistry, and in-office milled restorations. It really starts to open the door for the general practitioner to start accepting 3D printing and additive manufacturing as a reality in their own clinical practice. So to highlight a way that these things work, this is actually quite interesting. Okay, so when we look at digital dental systems, a lot of the newer camera systems are kind of working off a very similar principle called laser confocal microscopy scanning. And the way that these work, it uses essentially a focused beam of light or a laser, and it splits that beam of light or that laser and adjusts an aperture or focal distance to a known measurement. As the camera moves away, it removes unfocused images and comes up with a nice three-dimensional detail of surface texture and color. This principle is actually pretty old. It's been around since the late 1950s, and this was really used in the medical arena for research when we started looking at muscle tissue, nerve tissue, and those types of things to give a three-dimensional picture to some of the slides or some of the pathological or biological samples the laboratory would produce. Really, the first camera to introduce this was the iTero scanners back in 2007, and a lot of companies have started to kind of jump on that bandwagon of confocal microscopy as one of the most accurate scanning methods for intraoral scanners. Now, if you're unfamiliar with what's at the bottom right-hand side of the screen, that's a QR code, and I like to put these up there because I do have links to the text that which I'm referencing within the paper. But if I've got full access to a paper from a kind of a public access that I was able to find online, I actually create a QR code for anybody that's watching. So that way you can take out your smartphone, open your camera application, focus it on that QR code and take a really nice picture of it. And as you go to focus in on that picture, your smartphone should recognize and take you to the website where the full text link to the article can be found. Just as you're watching this webinar, it's a way that if you want to look at this article further, you can actually go ahead and look at the article that I'm quoting on this page. So how do digital dental systems work? Okay, so in order to understand additive manufacturing, we have to understand a little bit about how our image is captured. So I just chose a couple manufacturers of scanners out there and tried to look at, the basics, and it's much more complex than this, but what's the basic principle behind how it works? And from there, what's the universal file output? When it comes to additive manufacturing, what type of file are we going to get? Each individual manufacturer has their own proprietary files that they use that contain patient data and other things like that. But when it comes to additive manufacturing, we need a universal file output. So going through here, we have PrimeScan, iTero, Planmeca, Trios, and Carestream. And if you look at a lot of these, they use the principle of confocal microscopy or laser scanning. Okay, and along with the laser scanning and confocal microscopy, they're going to work in similar methods. One that is different is the active speed 3D video. That's actually using two cameras in the actual body of the scanner, and it's triangulating what we're seeing in the mouth by putting these two camera images together. So if you actually look at a Carestream scanner and take it apart, you can actually see the two little video cameras inside the handle. It's pretty neat. But when we look at universal file outputs, to me, that's what's important for the meat of this lecture. And when you see something that says STL, you can see how that's pretty universal amongst all of the cameras. When we go down to OBJ and PLY, that's something we're starting to see in some of the newer cameras that tend to be a little bit more open, or with the ability to work with many different CAM or computer-aided manufacturing systems. OBJ and PLY have a few distinct advantages over this STL file extension, which we'll get into in a minute. So why does this scanning technology matter, and why do I bring it up? Well, it kind of depends on what scanner you have, what different types of manufacturing processes are going to be open to you. So this is a study that compared 6 intraoral scanners on prepared teeth. Now, that being said, you can find probably hundreds of different studies on different intraoral scanners and different types of scanning modalities, and also different types of scans, whether it's implants, edentulous, partial arch, full arch. This is just one of the many articles out there. In this article, what it really looked at was the median trueness and the median precision. So when we look at these cameras, you can see that depending on what type of scanner we were using, we did have kind of a range of about 25 to 74 to 75 microns of accuracy between these prepared teeth using different types of scanning sequences. Now, any of these scanners are great scanners, and they're definitely going to do the trick for you. But what you have to ask yourself is, well, does it really matter what scanning technology I have? It really truly depends on what you're going for. Even the Emerald scanner, if you look at different studies looking at implants, it may have a little bit different number. So it really all depends on the individual application. But the takeaway point from this is a lot of the newer scanners we have in the market that have been released in the last 3 to 4 years really have an accuracy that meets all of the demands of our fixed prosthodontics, and is starting to get to the point when we see PrimeScan and the new Trio scanners where we can really do this for all full arch laser sintered bars and prosthetics that traditionally had to be done with a pickup type of impression with impression copings that were put together with Duralay pattern resin. So understanding that these newer scanners that are on the market all have a very high degree of accuracy, trueness, and precision, we also have to know a little bit about our file extensions, okay? So when we say STL, STL actually stands for something called Standard Tessellation Language. And within that standard tessellation language, we have high, medium, and low resolution. What STL files do is it takes a sphere and it converts it into a series of intersecting triangles that creates these things called facets. So if you look at the back of my PowerPoint presentation, you can actually see some teeth in the background. These are teeth that I scanned, converted into a wire mesh framework, and have them as my PowerPoint background. You can see that mesh intersection blown up about 25 or 30 times larger than the actual tooth that we scanned, to give you an appreciation for what an STL file actually does. Within the STL file, there's another couple cool things that it does. It actually gives you a basic global positioning of different dental arches. So if you scan a top arch and a bottom arch together, then what happens? Okay, well, if you scan a top arch and a bottom arch together, you actually get a basic global positioning of the top arch and the bottom arch in relation to each other. So a lot of our 3D planning softwares and a lot of our scanning softwares that come on our scanners will actually do this for us. So think of STL as just a basic black and white triangle. No matter what color representation your scanner shows, your STL file universal output is always going to be a colorless mesh network of triangles. Now, depending on if it's high, medium, or low resolution, this is what a basic sphere would look like on a high, medium, and low resolution type of STL. Again, depending on what you're trying to fabricate, if you're trying to fabricate crown and bridge work and send it off to your dental lab, well, then you probably want to export as what's called a high resolution STL file. If you're trying to fabricate a clear aligner for orthodontics and we're looking at 200 microns of accuracy as what we need for cross-arch stability, well then maybe that low resolution is a little bit easier file to give to your laboratory. But as our files are progressing and as our scanners become more and more open, we have things like OBJ files or object files. What an object file does is it advances the types of polygons that it can actually create within the surface. So instead of having a series of overlapping triangles that don't share any vertices or apices, we can actually have an OBJ file which can combine some of these triangles into different shapes of polygons. Now with this, the OBJ file tends to be a little bit larger, but it tends to give us a little bit more detail. I think one of the coolest things that's coming along is what's called the PLY file. The PLY file not only gives you increased amount of polygon data, but it also gives you a color image and surface texture. So with that color image and increased surface texture, we can take a scanner, export a PLY type of file, and pull it into a CAD/CAM type of planning software and see where the tooth starts, see where the gingiva starts. We don't have to worry as much about having a physical gap between our margin and our soft tissue because this PLY image allows us to use a little bit more of the color data that we picked up with our scanner. So when we look at STLs, they're the smallest size, but also the lowest resolution. For most of our needs communicating with the laboratory, an STL file is definitely going to meet our demands. But if we have areas where we have equigingival margins, sometimes we need to export as a PLY file. So that could be a larger size, but it's also going to be the most detail. When it comes to 3D printing, there's not many 3D printers on the market that we would have in our dental office right now that are multicolor printers. So in reality, when we're looking at doing 3D printing in the office, depending on what scanner you have, really all you need to have is STL or OBJ export. You don't have to have PLY. So if your objective with your scanner is to export for basic 3D printing, as long as you can export an STL file, you're going to be able to do 99% of the 3D printing needs you have in your office. If you do have something like a polyjet printer, which is very, very expensive, and they're more for an industrial type of larger laboratory that prints multicolor, well then maybe a PLY file would be a better file. So it's just understanding what file extensions we need to enhance our digital scanning capabilities. So what does this look like on a model? Okay, so when we look at a model, we can see the difference right here. So this is a scan of some teeth that I took in my dental practice, and you can see one of them is converted to an STL, and one of them is in the manufacturer proprietary file format known as what's called a DXD file. So it's very similar to that of a PLY, but this is just manufacturer specific. But you can see some of the loss of surface detail, some of the loss of our occlusion data, and overall, when we look at the actual shape of the teeth for making a removable restoration, there really isn't that large of a difference. So if we're making a night guard, this is an absolutely acceptable type of file export. So the left is an STL, the right, it would be an example of like a PLY image. So what happens when we change file formats? As I said, scanners have a proprietary file format attached to almost every manufacturer. So an easy way for me to explain this if you're new to the digital scanning world is like a DICOM image. So when we have our digital x-rays and we save a DICOM image and we send that DICOM file to another dentist, they have the ability to have the patient data, they have the ability to change the contrast, change the KVP, change the MA, and really play with that image as they see fit. If we go ahead and just save an image or export it as what's called a JPEG, well, the image is locked. There's not a whole lot we can do with it. And so we lose a lot of that specific embedded data in the DICOM. Well, the same thing happens when we remove our files, and we export them to an STL file. What an STL file makes us lose is patient data, margin data, color data, and the ability to edit the uncompressed image. So editing an STL file sometimes can be a little bit more challenging than editing it in our actual design software. So to me, that's one of the easiest ways to explain it. If we want to make changes to our digital files, one of the best ways to do it is in our digital scanner before we send it off to create a 3D printed product. So we have to understand that you lose some critical data for some purposes. So especially for crown and bridge work, if you do a really nice job of drawing your margins, but your scan doesn't have a physical distance between your gingival sulcus and your margin, sometimes you're going to have a hard time trying to reproduce that margin at the dental laboratory. Now, certain scanners, I believe like PlanMecca, have a ditching function that's actually built into the software when you export a crown and bridge file, which is excellent. And I think a lot of other manufacturers should probably do that as well. But those are some of the things that you lose. So when we talk about impressions versus digital scans, this is where we start to think, okay, I bought a digital scanner so I could send files off to the dental laboratory, so I can mill crowns in office, but I haven't really ventured into the world of 3D printing yet. Why would it be beneficial in my practice? Well, I ask you the question, do you really need a dental model? I think of all the times that I poured up dental models as study casts, looked at them, especially when I was getting started in CAD/CAM dentistry. I'd actually make a provisional matrix just in case my CAD/CAM machine broke down, and then I'd never end up using that alginate impression. So I wasted all of that money and had to dispose of that stone model. So if we're looking at it from the ability of saying, well, maybe we don't need the physical model and we can rely on the computer model for most needs, we can look at it almost as a fixed cost. We've already paid for our scanner. And depending on what scanner you have, it could be anywhere from $15,000 to $70,000. And I like to think they have about a 10-year life cycle. Okay, if we look at 260 working days per year, that works out to around, at the highest cost of a scanner, about $27 a day of a fixed cost. Okay, so no matter how many digital scans you take, that cost remains fixed. It only becomes variable when you talk about printing that model. But then when we talk about the physical impression, every single physical impression we take is a variable cost based on the ability of us to record that with either alginate or PVS. So if we're just looking at something like alginate, that can cost us about $7 for an upper and lower arch. We look at trays, adhesives, disposable trays, disinfectant, and finally stone to pour up those types of models. And then also you need the square footage for storage. So that to me is a variable cost. So inherently in having our digital scanner and some sort of CAM method, be it additive technology like a 3D printer, we now have the ability to kind of control our costs with our scanner from more of a fixed and reduce our variable costs. So overall, I'd say since I got my 3D printer, my ability to actually use a physical model has reduced drastically for things like surgical guides, for things like occlusal splints. I don't even print a physical model anymore because our 3D CAM software is so robust and so accurate. So when you look at that and say, well, okay, that's pretty interesting, but what are my basic return on investment questions that I have to ask on digital dentistry? So one of the first things I say is, well, if you already have a digital scanner, in my personal opinion, a 3D printer is kind of a no-brainer option. But if you're still asking yourself that question, you say, does this technology cost you less than your lab bill? And would the addition of that 3D printer really make the difference? So again, I've listed this in the references at the end of the presentation, but if you have your smartphone, you open your camera app and focus in on this QR code, this will actually bring you to a dental economics article from 2006 that talks about the reduction in lab costs of having something like chairside scanning and chairside milling. When we look at 3D additive and subtractive technologies, does it provide an added benefit to my patient? So that's one of the main questions I have as well. And can you reduce remakes and increase your accuracy? I think of this especially with something like an occlusal guard or a guided implant surgery. Am I going to reduce the ability of an unforeseen ill-placed implant, and am I going to make my restorative job easier? So here's another link to an article from Dental Economics again, looking at a group from Pacific Dental Group, looking at their remake rates just for subtractive type of technologies in the dental practice. So as you start asking these questions, can additive be the same way? Well, to start getting into 3D printing as an important part of our dental practice, we have to understand that additive manufacturing drives that innovation because it allows us the ability to have complex designs and design freedom. And we actually have very minimal waste material when we're doing 3D printing. We only cure or extrude the material we need for the 3D printing process with very minimal support structures needed to create our dental models. So there's absolutely an inherent cost savings over something like a milled block because we only use the material that we need. So when we talk about ease of access, 3D printers since about 2003 have come down drastically in price due to the availability of cheap light processing units and increased software manipulation. So in this video here, you can see that I have a Formlabs printer, and this printer, we'll talk about the design here in the next couple slides, but it's going through and it's printing me a couple night guards in my build platform using a light processing unit to go around, and you can see it slowly curing different layers with the laser to actually fabricate a couple occlusal devices. So to start to understand our scanners, our technology, and why it might be important to control our fixed and variable costs, now we have to look at different types of 3D printers that are available. So breaking down the printing tech, usually we have something called a resin tray polymerization type of printer, which uses a liquid resin cured by a light source in a vat. And those typically break down into DLP, LED, and SLA types of printers, or digital light projection, light emitting diode, and stereolithographic types of printers. We also have material extrusion printers, which is what we call a fused filament printer. These typically have a coil of material heated and extruded through a nozzle. This is what a lot of people think about when they think of 3D printers, because this is one of the cheap hobby printers that you can buy on the market. They can actually be one of the most accurate printers too, if you spend the money and get the right 3D printer. And then we have material jetting printers, where they use little drops of liquid onto a build plate, almost like a inkjet printer that we would find on our desktop for just printing some documents. This is something called a polyjet type of printer. These are really neat because based on the dots per inch types of resolution, we can get very, very fine microns of accuracy. So typically when we look at things like DLPs and LEDs, they're going to cure in a certain way that's going to lock our relative accuracy into like a 50 micron range. As we start to get to SLA printers, where we have a little bit more freedom of movement based on a laser and based off of a movable mirror, we tend to have a little bit higher relative accuracy. And then our fused form filaments and polyjets can get even more accurate. Now with polyjets, the neat thing about them, and I don't talk a ton because we'd have to have a whole nother lecture on introducing what's available from the dental laboratory side, but these printers have the ability to print multicolored and very complex, intricate networks. So we don't need a lot of supports because it can print unsupported areas a lot better than something like a DLP or LED printer would. So when we look at this, one thing to remember from this type of 3D printer chart that we created is increased accuracy can imply slowing printer times as a general trend. So typically the relative accuracy dropping typically means that the print isn't going to take as long. And what you're trying to manufacture should dictate your scanner and your printer. So for most dental needs, printing at 100 microns is absolutely more than accurate enough. So all of these printers that I've listed here would meet our basic requirements. If we're looking at the scanners we talked about earlier, and we looked at that one article that 75 microns was our least true and accurate scanner. Well, still, that meets the needs of the majority of our removable dental needs. We start to get into full arch fixed implant types of bars, well, then maybe we need to have a little bit more accurate printer. Um, and so we may have to be more selective on the printer, maybe something that's 25 microns in accuracy, and maybe have to be a little more selective on our scanner, something that has 25 to 40 microns. So the top two that were on the list when we talked about accuracy and trueness. So depending on what you're doing is really going to dictate technology that you need. So now we have to talk about selecting the right resins. So I created this little kind of flow chart to kind of help people out because this can get really confusing when you're new to 3D printing. And so the basic question you need to ask when you're looking at a 3D printer is, does this resin have to go into the patient's mouth? If the question is no, well, 3D printing is very, very inexpensive and a very high return on investment because you can use a very low cost resin that just meets your minimum thickness requirements, which would mean, if we're printing things like clear aligner therapy or clear aligner trays for orthodontic movement, we can have a resin that prints at 200 microns, which generally is pretty cheap. If we have something that needs to go into the mouth, then it gets a little bit more complex and a little bit more expensive. We have to ask the question of how long this has to go in the patient's mouth. So usually what we say is, well, is it going to be greater or less than 24 hours of time? If it's going to be less than 24 hours of time, we can look at something like a class 1 biocompatible resin or a short-term resin. This is typically what we see as those orangish or amber surgical guides you get back from your dental laboratory. That's why I try to make this kind of an amber type of color. And they're indicated for intraoral use of less than 24 hours. So in all of the ISO standard tests they run, there is no biocompatibility issues in the short term. They tend to be maybe a little bit less expensive. Now when we talk about greater than 24 hours, we're looking at our class 2 or class 2A biocompatible long-term resins. So these are long-term. They're defined as a constant contact for up to 1 year with the biological tissue. So this is something like crown and bridge resin. This is something like an occlusal splint. So some of the resins out there that are, denture teeth are a little bit different. They don't necessarily fit into this category. But if we're looking at something like denture base resin, intraoral splint resin, those kinds of things tend to be very expensive per liter because they have to meet a little bit more rigorous biocompatibility type of test. So Sprint Ray actually had some really neat graphics on their website that I was able to find to kind of show the basics of what is stereolithography. So when we look at a stereolithographic or SLA printer, you can see that we have a laser light source and we have a movable mirror. Okay, so lasers and mirrors are contained in what's called a light processing unit. So one of the common ones on the market is Formlabs printers. They have a light processing unit that has something that works along these basic principles. The laser cures in a path each individual point on that individual layer. So as you watch these print, what you're actually going to see is a laser looking like it's zapping the surface of your model, and it's building it from the base to the top of the model. So it actually builds the model upside down. So these liquid photopolymers in a vat are selectively cured and activated by light polymerization. Typically, these happen in the wavelength of around 385 to 405 nanometers. So these are very, very accurate scanners, and their resolution is really dependent on the thickness of the laser beam. So if that laser beam is, 40 microns, and we can angle our model, we can get down, based off of the way that laser is going to reflect off the mirror, to about 25 microns of accuracy. So they can be very, very accurate, but when they get that accurate, they tend to really slow down. Digital light projection is kind of neat. Think of this kind of like your projector for your, those old TVs we used to have before the advent of flat screen TVs, and you had a projector in the back that went onto a screen and projected a surface. So digital light processing is actually a really cool type of technique because it uses a large arc of light to polymerize a resin vat one slice at a time. So instead of following an individual path, it's going to divide your 3D printed product into different layers of 3D printing, or one slice at a time. So it's nice because that DLP can typically have a larger build platform, and every layer or slice is what matters, not how many passes the laser has to make, but just how many individual slices. So these tend to print very, very fast. So things like Moonray and Sprint Ray printers, those can print very, very quickly, and they tend to be very low maintenance because there's not a lot of moving parts. So again, it still cures a liquid vat of resin. Now, when we look at LCDs, these are the little kind of hobby printers you can find in the market, and now they're getting to be more and more advanced, but these can actually be extrapolated and used in the dental world as well. So what an LED type of printer is, it uses a light emitting diode to cure, much like a DLP printer would, but directly with an LCD screen. So these typically will cure in the range of about 405 nanometers, and typically what you find with these cheap printers you'll find on Amazon or eBay or other kind of Facebook 3D printing groups is they're pretty much a cell phone screen. They'll take a cell phone screen and utilize that cell phone screen to project these different slices. So you tend to find your build platforms are very, very small, about the size of a large cell phone. Now, some manufacturers are starting to come out with really large LCD printers, and the cool thing about them is they're starting to become monochromatic. So when we had an LED, like a cell phone screen, we tended to have loss towards the edges. So prints towards the edges of our build platform would be a little bit less accurate, and we'd have a little bit higher print failure. But now with our newer printers being monochromatic LEDs, they project a narrower band of UV light. So it's pretty cool. Now with newer LCD technology being even cheaper as well, we went from 2K to 4K resolution on some of these printers. So they can be very fast prints when they're monochromatic because they're a very efficient process. And with 4K accuracy, we can have accuracy less than 50 microns. So these printers used to be kind of expensive and used to be very difficult. Like when they break, you have to replace the entire LCD screen. But overall, they're becoming a very low price point and a very good way to kind of get you into the 3D printing world. So the 3D printer I showed on the front screen of my presentation was actually a small LED printer that you can buy for about $250 online that can utilize a lot of our dental resins for printing things like orthodontic models and surgical guides. So you probably heard me mention something called trueness and precision a few times. And I know it probably goes back to statistics, and this is just a really basic review of what that means. So when we look at trueness and precision of a 3D model, we see that there's standards of error in our scans, and there's standards of error in our print based off of the slice thickness of our models. But looking at this study that I quoted below, essentially what they did is they compared to a reference cast, or the trueness of what the actual intraoral scan and 3D printed model gave us. And what we found is the printed cast had a mean deviation of about 106 microns, where the stone casts had a mean deviation of about 187 microns from the reference model. So what we find is 3D printing, if we use it a very accurate scanner, can actually have a little bit better trueness than trying to reproduce, take an alginate impression, and then pour a stone model. If we compare multiple pours to multiple prints, we find that the printed cast mean standard deviation was about 150 from model to model on the printer and 180 on the stone cast. So it wasn't really with a statistical difference, but still you can see that 3D printing technology has come a long way and is getting to the point where it is just as accurate or slightly better in the means of trueness and precision based off this ISO standard as just pouring up a model by hand. So now, we talked about model costs, right? So when I ask about the return on investment questions, can it increase our ability to be more accurate and give us a really good service to our patients? Well, that shows us right there, it's going to be as good or maybe slightly better than the conventional method of pouring up a model. Well, now let's look at if we just use a 3D printer for model costs, what is this going to save us? Now, if this were to be a PVS impression, different story because this cost goes up significantly. So if we're looking at just an alginate impression for a study model, what we calculated in our practice is it costs us about $3.50 per arch from the start of that impression to pouring it up to a stone model. When we look at our model cost for a 3D printer, it's about $1.50 per model. So if you're only using it to replace alginate impressions, you're going to have to get about 2,400 models to pay off your investment. Now, that being said, if you're using these models for digital smile design and digital mock-ups on patients, well, then that payoff might come a little bit faster. So even though this is a great way to start on 3D printers, this isn't where you should stop with your 3D printer. This should maybe be what gets your feet wet and gets you used to the 3D printing process. But I'm going to show you some methods that we can actually reduce that return on investment down to as little as 6 cases on our 3D printer. One of the easiest ways to introduce this, in my opinion, in your practice is the 3D night guard. And it all starts with your scan, right? So once you have your scanner for doing different types of fixed dental prosthetics, we're then going to take that, depending on what type of scanner we have, whether it's a Trio scanner and we're exporting as a 3-shape image, or a Densify scanner, we're exporting as a DXD, or any scanner on the market, and you export as that universal file output of an STL file, we can actually go ahead and start printing our 3D night guards in-house. This is a great way to recapture your return on investment on your 3D printer. So I have a military background, and we have some publicly available military documents that you can find on Google, one of them being something called TB-Med 148. So that is essentially our prosthodontic standards for how we calculate how much time a laboratory process should take one of our technicians. Then if we also look at some of our different people that we hire based off of data you can find on things like USA Jobs, our CAD/CAM auxiliary specialists, which can do digital designs for us, make about $32,000 a year, and our dental lab techs starting make about $45,000 a year. Now, that varies, and it's a variable cost based on years of experience, medical insurance, where you live, signing bonuses, but for the basics of what you can find online, this is very rounded numbers. Okay, when we talk about clinical value, or how much time a process takes in the laboratory, we talk about what's called the CLV, or the Clinic Laboratory Composite Laboratory Value. So this is an example of what that means. So why do I keep this slide in here? Well, I think you have to ask either 2 questions. If you do this process in-house, how much time does this take you to do it? And that's a very important calculation to understand return on investment. So for us, for an in-house lab, we use this calculation assumption. If we're sending it off to an external lab, then obviously we just need to know what the external lab is charging us, and are we saving money based off of our time and our supplies. So looking at our clinics, we found, not breaking these down completely for you, it costs us about $20 in materials to fabricate a traditional night guard, but then it was $122 in labor. So it really costs us about $144 to fabricate our total cost for our night guard. Okay, when we looked at our 3D printed process in-house, and we looked at our CAD/CAM auxiliary, which makes a little less money and it takes less time, it was about $26 per night guard in labor and about $16 in material. So about $42 in total cost. So we're saving around $100 or slightly over when we're looking at 3D printed night guards. So when we look at the cost of the printer, they range, but I would say to get a really good setup that can set you up for printing biocompatible resins and have a really nice defined workflow in your practice, it's going to cost you about $6,000. If we look at something like a biocompatible resin, it's going to be about $300 to $400 per liter, and we can get about 30 liters or 30 night guards from 1 liter of resin. And judging from the fact that we can save about $100 per night guard, in about 60 night guards, we start to pay off our initial investment of our 3D printer. So that's much more reasonable to me. 60 night guards looks better than 22 to 2,400 impressions. So a night guard, it's fun too. I give my assistants the ability to do the scans on these. I give my assistants the ability to take a crack at designing them, and they find it's really fun. It's a delegatable task that saves us a lot of money and really pays off our 3D printer for other types of projects as well. So when we get a scan though, it's not like we can just take that scan and instantly print a model. We have to take that mesh framework and we have to convert it into something that our 3D printer can read. So it's very easy nowadays though. Some of the scanners, I believe Plan Mecha is one of them, that has a direct export that has a printable 3D STL file. You can pay for additional software from the company like Dentsply Sirona, 3Shape, other software companies, and they have the ability to create a meshed model for you that's 3D printer ready. You can use freeware from a third party, and I'm going to show you essentially how to do that here in a couple minutes. We can use 3D printer slicing software like you see on the right hand side, but ultimately we have to understand that when we go to print a file, we have to have either an STL or an OBJ, or object type of image. When we start to look at color printing, PLY is something that we can export to a color printer. So as we move forward in our dental practices, it's not just the fact that that 3D printer is going to provide us a basic product with the benefit of seeing that tangible cost as a reduced lab bill, but what that's also going to allow us to do is take a scan or a model and digitize that model to attach it to the patient's x-rays or attach it to the patient's patient management system. So I think that digital models really makes this a possibility. And it takes us from this type of environment where we have all of these paper charts and we have all of this square footage to store orthodontic models for 10 years, and it takes it all down to a hard drive, or even better, a cloud. So when we look at our future goals of what we want to accomplish, we're also looking at a smaller dental office that can provide more services. Cost per square foot goes down, your overhead goes down because all of the bills that are associated with it go down as well. So that ability to shrink your lab down to a 3D printer in a mill really shrinks your square footage of your overall practice. So now what I want to do is take you out of this presentation for a second, and I want to take you in to show you what a 3D mesh actually looks like and how you can use a very low-cost product to actually create a night guard. So this is actually a copy of my own teeth, and I'm going to go ahead and take you out of this software, and we are going to go ahead and open something called Blender. So in Blender, we have the ability to actually import some of our models. So in Blender, I'm going to go ahead and I'm going to import my upper jaw and show you how we're actually going to take this and make a printable STL file. So as you can see from this model here, if we rotate my model around, you can almost see into my model. When it looks like this is not a printable surface. This internal aspect and external aspect of this STL file occupy the exact same physical space. There is no physical thickness to this model right now. This is just a series of triangles that accurately represents the surface of my teeth. But if we were to invert this image, it would also give me a perfect negative of what my teeth look like as well. So in order to 3D print this model, what we need to do is add a base. Well, this application called D3 Splint does a really nice job of adding a base, essentially with a single click. All we have to do is come down here to Simple Base, click OK, let the computer go through about 15 or 20 seconds of processing, and it's going to go ahead and it's going to add a base to my model for me. The nice thing about this software is you can install it just about on any scanner that you have. It requires very limited space. I usually install this on my backup drive, so I have a C drive and a D drive. And what I actually do with this is I can design my night guards, or I can print my models directly from the chair. So you can see right here, I now have a filled in model that's actually exportable. If we went to File, Export, STL, and now we could actually 3D print this model for the cost of about $1.50 and one of the 3D printers we talked about. Now, if I want to go ahead and create something like a night guard, it's just as simple, and I'm going to walk you through that entire process. So as we talked about earlier, if we import our upper and lower models as STLs, STLs not only are a wire mesh framework of the teeth, but you can also see it records how my bite actually came together. Now, these softwares make it extremely simple to delegate. It walks you through step by step. We can select which jaws are active jaw. Then we can left click and select which jaws are opposing jaw. If we follow the directions on the right hand side of the screen, what we're going to do next is we're actually going to go ahead and select some landmarks so we can put this onto what's called a virtual articulator. So I imagine that I've now, 5 minutes after scanning the patient, chairside in my scanner, I have a port up mounted model on a semi-adjustable articulator. I physically can't do that process that fast out of Alginate. Then what we're going to do is we're going to go ahead and we're going to change our pin setting. Because we're going to use this for a occlusal splint, we want to have about 2 millimeters of posterior opening. So we're going to go ahead and open the pin about 5 millimeters. Now, the scanner that we use actually has an accuracy a lot closer to that of a polyvinyl siloxane. So overall, imagine I took a PVS, maxillary mandibular impression, and now I've mounted it on a semi-adjustable articulator. This is getting very, very accurate in a very short amount of time. I can then check to make sure that I have about 2 millimeters of interocclusal distance, which here I have a small intersection at 1.75. For demonstration purposes, we're just going to keep going and finish making this type of occlusal splint. I can then survey my model. So now I'm mounting this model, I'm looking at it, and I'm deciding where my undercuts are going to be. So from here, we're going to go ahead and we're going to save our file. And we're going to create a model that has all of the blockout resin already on it. So overall, this is pretty darn cool, right? So we have a model that has now been mounted. We've added blockout material, and now we're going through and we're going to go ahead and make our digital night guard. So you can see here, now here's our model that has our blockout. So to mark our splint outline, it's even easier. We're just going to go ahead and start clicking points. And we're going to make just a basic monoplane splint for the sake of this demonstration. So we can click, or we can hold the shift key, and we can drag a line all the way around to decide where we want our splint to start, we want our splint to end. Here we go. We'll connect our endpoints and we'll click next. Now we're going to tell the 3D printing software, I want you to go ahead and make an occlusal device in this spot right here. We'll click next one more time. And now we'll go ahead and mark our shell. We'll go ahead and mark our minimal thickness. We'll mark our occlusion. So this is where my jaw is going to move in relation to the maxillary teeth. Our mandibular teeth are going to move past our maxillary buccal cusps. Our maxillary teeth in working and non-working movements are going to move past our mandibular teeth on the lingual cusps. We're going to verify that we like the way that this comes together. And then we're going to click commit. We're going to go ahead and we're going to do our what's called wax rim, and we're going to fuse those together. We can then mark all of our contacts. So this is something that I do chairside with our patient, right? And this is a great way for me to talk to my patient about the wear facets. This being my teeth, I know I'm a stressed individual, so you can see all the heavy wear facets I have in my teeth. I'm definitely somebody who needs an occlusal device. And so as I start marking my contacts, you'll see that this computer algorithm is starting to generate a functionally generated path where my articulator is going to start to move. So now, here is a basic monoplane occlusal splint, and now we can run it through semi-adjustable articulation. So now here, before I could even take an impression back to the laboratory, and probably before I would even have both arches of my polyvinyl siloxane even set, I've already got this mounted on the semi-adjustable articulator. I've already made my hard acrylic outline, and now I'm going through and I'm doing all of the fine adjustments on the articulator. Now from here, we have everything that we need. We have our splint, and now we're going to go ahead and we're going to smooth out any of these last couple areas we have that are high in contact. Now I have a really nice flat plane occlusal splint. We'll finalize the splint, and now we'll go ahead and we'll export it to the desktop. Now in a matter of about 5 minutes, we have a fully exportable, 3D printable monoplane occlusal device that'll take about 1 hour to print. But the nice part of this is we can do all of these chairside and print them at the end of the day when we go home. So overall, that task with that software called Blender or D3 tool is a very low-cost introductory option to getting into your own splint design. Now, depending on what manufacturer you have of your 3D scanner or your 3D printer, there might be other options available for you through your manufacturer. So that's just one example of one open source software you can use to do either a based model of an STL framework or to do a maxillary hard night guard. Now, digital limited orthodontics. Now, what digital limited orthodontics can bring to you as well is something very, very minor. This patient presented and didn't like tooth number 10, how the lateral incisor was excessively flared. Now, this is a case where the patient didn't want to go through conventional orthodontics. This was post-orthodontic relapse and a very, very easy case to get started with digital limited orthodontics. So, if you can see the arch form here, this patient needs a little flaring of tooth number 8 and 9, so we can actually create a little bit of arch length or room for tooth number 10 to be brought back into our dental arch. So again, we can take all of our standard orthodontic photos. We can go ahead and create our STL models to export to one of our orthodontic planning softwares. There's a ton of different orthodontic planning softwares on the market right now. One of the ones that I use is Blue Sky Plan because it's very low cost, about $25 per patient, and it'll create multiple steps, buttons, attachments. But ultimately, for something like digital limited orthodontics, this is something that creates a very quick payoff point for our 3D printer. So what it does is you can see we had a little bit of interproximal reduction, a little bit of movement to our other teeth. We use a multi-layer clear aligner material. There's many on the market. The one I was using was Zendura FLX, but there's many others on the market. And then it prints a series of models with minor tooth movement along the way. So you can see here, it even breaks it down, the software, into different stages of movement. Okay, so we typically limit our movement to about 0.25 per dental tray. And because we have a multi-layer material, this tooth will actually get moved based off of the resiliency of that plastic or elastomeric material in our clear aligner product. So it's important to select a clear aligner material that's actually meant for orthodontic movement. But one kind of cost point to think of is, okay, well, how much is this going to cost versus sending it off to a lab for a limited, Invisalign or ClearCorrect or some other clear aligner therapy? How much is this going to cost me in my office? Well, it's going to cost you about $4 to $6 per tray and about $25 for the treatment plan using what I used. There's different companies that allow kind of a blended model, or they'll actually plan it for you, send you back the models, and all you have to do is do the printing, which again utilizes your 3D printer. You may have a little higher amount of aligners you'd have to do to pay off your 3D printer. But if you do everything yourself, including your treatment planning, you can see how inexpensive this truly is. So if we're assuming 24 trays or 12 trays per arch, we only really have to do about 6 clear aligner cases to pay off a really nice 3D printer setup. So this is a very, very good way to utilize your 3D printing technology and also increase the effectiveness of your intraoral scanner. So you can see here, here's my proposed orthodontic movement. It was about 3 hours of printing. And you can see before and after. Very, very straightforward. The patient was thrilled with this limited orthodontic movement, and it was overall very simple to achieve. So when we look at this, it took about 1 to 2 hours of my time and cost me about $45. Okay, so I'm not going to talk about what you would charge your patient for something like this, but I'll let you decide that for your own practice, what you charge a patient for something simple like this. Now, even more complex cases are very possible, and there's many different orthodontic softwares out there that can allow you to do it. But overall, another way to incorporate 3D printing into your office to go beyond just the chairside milled restoration for your intraoral scanners. One of the last ways that I really like to incorporate this is our minimal flap and guided implant placement and immediate CAD/CAM provisionals. This utilizes every piece of technology that we have in our dental practice, and it really drives home the point that we get very accurate results. We get the implant exactly where we want it, and we can get a provisional restoration that really drives home soft tissue support and overall aesthetics. So the system that I use is Biomet 3i, and I use a tapered navigator system. Now, there's many different systems out there. I'm not going to say one is superior to the other. This is just the one that I use. And here's an example using my planning software, Blue Sky, exactly what this implant would look like. When we talk about $25 per patient, if we have the cone beam and we have an intraoral scan and bring it into this software called Blue Sky, what we can actually do is plan this dental implant out and break this down into a series of drills, all the way from the tissue punch to our analog mount, and it gives us all the part numbers we need so we can cost out exactly what this is going to take to place this implant. So designing the guide and 3D printing it, I used a Formlabs Form 3B printer and surgical guide resin, but overall, when we do something like this, you can see we get very nice implant placement at the end, and it's about $43 for me to plan this in-house, from the surgical plan, for me to actually plan the surgery, me to get the exports, me to buy the guide tube, me to print the resin and export the STL files. Just doing some basic searching at laboratories, and I'm sure there's labs that are more expensive. There's labs that are probably a little less expensive. But for a lab to plan a single tooth implant for you to approve it, and for them to send you all the materials back, it looks like it averages about $250. So again, if you look to incorporate surgical guides into your practice, this is about 25 single tooth surgical guides. So it's a very, very low cost point. And it's about a 1-year payoff, right? 25 implants per year is a very reasonable start for you to get started with dental implants. So if you incorporate night guards and surgical guides, your price point for that 3D printer gets paid off very, very fast. And overall, these 3D printers are very reliable. So you can see how this is really helping out your chairside scanning efficiency beyond just the single tooth or multi-unit crown. So if you're not sure what a guide sleeve is, different implant manufacturers have these guide sleeves with little keys in them, so that way we know exactly where the implant will stop, so we know where the hex will end, so we can actually, if we wanted to, plan the crown ahead of time, and once the implant is placed, we can place the crown on there assuming we have the right torque value. So for this system, just to walk you through the basics, it's very straightforward, right? It starts with a soft tissue punch or a small tissue incision. We then have something called a cortical perforation to go ahead and get started. Again, this is done directly through the surgical guide with a class 1 biocompatible resin in the mouth. We then go ahead and use our twist drills to gain our length. And the nice thing about these twist drills, whether it's a keyed or a keyless system, is it bottoms out the twist drill. So once you've done your planning ahead of time and you ensure that you've got the plan in the right location, even though we have 9 drills, this entire sequence with radiographs takes me about 25 minutes to place a dental implant. We then have our countersink drills, which allow that if we want a subcrestal placement based off of what the computer program sees, it's going to ask us to use the countersinking drills. Depending on our bone density, it's going to ask us to either only use one quad shaping drill or multiple quad shaping drills. There's other implant systems that are out there that you only use essentially 2 drills for the entire process. So this is just giving you an idea of how that 3D printed process really gives you ahead of time exactly costing out how much this implant is going to cost you in your practice. Looking at our implant mounts, you can see how the notches line up. So if we planned our crown ahead of time, we know exactly where we have to have our crown lined up in order for our restoration to fit. So for me, when I do these types of cases, what I like to do is place the implant first, ensure that I have the adequate torque value. I then make a little partial thickness release, so that way I can push the tissue buckle slightly, but that implant pretty much goes exactly as planned, directly in the center of our hole. I then put on what's called a scan body, and I put on a scan post. And then from there, we go ahead and fabricate just a provisional restoration from the patient. And overall, from time of anesthesia to final seating of the long-term provisional restoration, it's about 1.5 hours. And you can see how we can control the occlusion to make sure it's completely out of function, so we can support our soft tissue and have a very predictable, safe procedure. So when I talk about cost, it not only saves costs, but it provides an added benefit to our patient, because now that patient isn't having to walk out of your office without a tooth. And we were able to plan all this out ahead of time, so when it comes to our informed consent for our patient, they understand exactly what they're going to undergo for that day. So here's the before and after that same day for the surgery. So in conclusion, we went over the basics of our complete CAD/CAM system. We understand that computer-aided design and computer-aided manufacturing has common file exports that can affect the CAD and the CAM processes. We reviewed the basics of 3D printing technology as an extension to our in-office CAD/CAM systems. And ultimately, we discussed how the utilization of additive technologies, utilizing different resins, can quickly pay for themselves and augment your digital scanner and take you beyond the milled restoration. I show this picture behind you to show you what happens when we don't necessarily have 3D planning. Sometimes we get cases that we inherit that didn't go as planned for a patient. This is a distraction osteogenesis device that was placed but didn't really go through the 3D planning process that I like to go through now. So when you look at cases like this is what we try to avoid. We try to reduce the amount of unforeseen medical errors or preventable medical errors that come into our practice to make everything more predictable for our patients, cost less money, overall have better outcomes, and make happy patients. Overall, here are my references, and I'd be happy to answer any questions at this time.